This is a horizontally opposed 4-cylinder Lycoming engine. Basically two manufacturers in this field, Lycoming and Continental. They're essentially the same. Your prop is attached to a crankshaft inside this engine. Very important component in the engine. It's the heaviest part of the engine, really. Okay? This is your crankcase. Right? This section is your crankcase. Top and bottom. Inside this crankcase, very simple. You have a crankshaft. And in the Lycoming, and I'll tell you the difference between Lycoming and Continental. Crankshaft in the middle, camshaft on top. Camshaft is what moves these rods that are inside these tubes that opens and closes the valves inside the cylinder. Okay? Cam turns, opens intake valve. In the intake valve, air and fuel go into the cylinder. Combust. The exhaust valve now, on the millisecond that it works, the intake valve now closes, and the cam pushes this rod and opens the exhaust valve, letting the combustion come out of the cylinder through this pipe into the exhaust system. This is your muffler, just like in a car. The muffler is actually inside here. Outside of the muffler is a heat shield. Okay? And we'll get to that in a second. So this is your cylinder. It's a 4-cylinder, horizontally opposed engine. Horizontal because the pistons are going this way. In a car, they go up and down. Okay? Up and down wears the crank out much quicker. In a horizontally opposed engine, there's less wear and tear on the crank. Why?
You're not fighting gravity?
You're not fighting gravity, and you're using the full spectrum of that crank. Where in a V engine, you're going to wear the top and the bottom out of the crank, of the bearings. Okay? So, you have a crankcase, 4 cylinders. Comes in 4 and 6. No difference, 4 and 6, just 2 extra cylinders, more horsepower. Okay, these are big cylinders. They're not like in the car. The pistons are probably that big. The piston in a car is generally about that big. Okay? These are big cylinders. They're redundant, strong, withstand temperature changes. Where in a car, it doesn't deal with the temperature change differently because it's liquid cooled. These are air cooled. Thus the importance of the spinner flowing air into the engine to keep it cool. Okay? In a liquid cooled engine, there will be ports in the cylinders. And in those ports, liquid will cool the cylinder. The only thing cool in this cylinder, so it doesn't overheat, is the air flowing through it. You climb too much, you heat up the cylinders. What cools the cylinder? Fuel. Fuel cools the cylinder, believe it or not. Fuel cools the engine. That's why you're running full rich when you're taking off. Okay? The fuel actually cools the cylinder. You don't need that much fuel because it'll work with less fuel, but the fuel actually cools the cylinder. You're burning a lot of fuel because half of it's getting just thrown out of the exhaust system. Not that it's all being burned so efficiently. They're not that efficient. Okay, it's old technology. Okay, but that's why it works. So, in this crankcase, there's torques. This case, you know, when you climb, your temperature's getting cooler. Your engine's getting hot. The engine contracts, expands, contracts, expands. These bolts aren't tightened down to life. They're tightened down to a certain torque specification so that when you climb the altitude and the case starts expanding and contracting, it doesn't crack. Okay, so there's a lot of movement here. So when you're looking at the engine, you want to look for cracks along this line. Okay, you want to look for severe oil leaks along this line. It's 2 halves, right? Split right down the middle. Okay? If there's a failure, you're going to see oil up in here. Okay, this engine's nice and dry. Everything's operating the way it should be. Okay? So there's your cylinders. You can see this is your oil pressure regulator. This little thing right here. Okay, that's what regulates the oil pressure in the engine. Apparently this one likes to run high. It's got a high oil pressure. There's been complaints about it. The high oil pressure is not going to damage anything. Low oil pressure is going to damage things. because there's channels in here that the oil is flowing to provide lubrication to this crank that's turning. There's a crank, and then there's bearings around that crank, and they're just about touching. There's like a hair in there where the oil rides inside between the crank and the bearing over it. Okay? Why are cold starts so critical when you're starting these engines in the winter? The engine's been sitting out all night, everything's cold, the metals in here are different. There's aluminum in here, there's magnesium, there's steel. All of these things contract and expand at different rates. When you turn that engine cold, the oil is so thick that for that millisecond, 2 seconds, there's no lubrication between that crank and that bearing. You're damaging the engine, okay? So, old timers, again, make sure everything's off. It's always advisable to get up here and turn the prop. Got nice compression. You see, you're also testing the compression, right? That was a little less, right? That was nice and stiff. In the cold, it's always going to be a little stiffer because the oil's thick. In the summer, the oil's thinner, so it's going to turn a little freer. Okay, give it a couple of turns. Give it at least 4 to 8 turns. Get the oil working. The oil that's been sitting cold all night. Okay? That will help start that engine so much better, and you're not damaging the engine. And you're also checking compression. If you turn this prop, and you can just like that, well, something's wrong here. There's no compression in that cylinder. I probably shouldn't fly this airplane. Right? There's 4 cylinders, 4 turns. That click you're hearing is the magneto, the impulse coupling in the magneto, which initiates all the spark in the engine. Okay? This one's got nice compression. Good to do. It helps preserve the plane. Also lets you know that you have compression happening inside. Where's the compression? You got your piston. Here is a standard, this is a Lycoming cylinder. Same cylinder that's here. Okay, this is your piston. This is where the combustion is happening, right? These are your rings. There's an oil scraper ring, which sort of cleans the cylinder as it goes up and down. All right, this compresses in there. You see it won't go in just by itself. As the engine wears, as the cylinder wears, these rings wear out. And that's what reduces your compression. So this has to be compressed inside the cylinder. And as this goes up and down in the cylinder, that's what's creating, when the explosion happens in here, if you look, there's your valves. You have an exhaust valve and an intake valve. I was telling you before. One lets the air and fuel in. The spark plugs ignites that fuel. The exhaust valve opens and lets the exhaust out. Okay? So as the combustion happens, the explosion pushes the cylinder back, making the cylinder on the other side press forward. That constant rotation is what's creating the energy to turn the prop. Okay? Thus, again, the horizontally opposed. You got one cylinder, one piston basically pushing the other one on the other side back. You see? There's always an interaction. You start an airplane and you start getting an RPM that goes, that means one of these cylinders has failed. Okay? It's not a misfire, it's not bad fuel. You'll see a dramatic decrease in RPM. So you'll be at 1,000 RPM and the RPMs will drop down as it passes a dead cylinder. So if the firing order, which tells you right here the firing order of the engine, okay? Firing 1, 3, 2, 4. Okay, it fires cylinder 1, then cylinder 3, cylinder 2, and then cylinder 4. They're opposed to each other. As one comes out, the other one's coming in. As the one on the other side goes out, this one's coming in. So you see that constantly, it's like a tug of war. All right, that's what makes that crank turn. All right, because on here is going to be a connecting rod. That connecting rod is attached to this crank. So this is turning, and that's what's making this cylinder go, the piston go in and out of that cylinder. Okay, and here's your lead. Here's your lead of your low lead. That's all lead right there. Right? A lot of lead in this fuel. Very bad. Now, a common problem with these planes, especially Lycomings, in high heat, this lead that's building up in here will actually jam this valve from opening and closing. We're not going to be able to do it because it's still on a spring. Okay? There's lots of ways to lose compression in a cylinder. Either the rings have worn out, not creating that press in here, that rubbing, right? Or lead can actually jam the valve in the top of that cylinder, right? This is the head of the cylinder. Everything up here is the head. This is the actual where the piston rides, right? In the head of the cylinder where the valves are, the valve stem, right? The valve is flat, has a stem that comes out. That valve is inside a guide. It's just like a bushing. And the valve rides inside that guide. That's what makes it, you know, that's the material that's going to give, so you don't wear out the head of the cylinder, right? What happens? If you don't lean out this engine, especially on the ground in high heat, the lead builds up in that guide, and then all of a sudden that valve is just going to get stuck there. And you're either going to break something or you're going to lose compression because now that valve is stuck open. So any combustion that's happening in there isn't being held to push that piston back. It's just escaping right outside the valve. That's why it's important that you lean these planes out in high heat on the ground. You don't need a lot of fuel, especially on the ground. Okay? Start your plane in high heat. Pull your mixture back. You're going to see it starting to run rough. And just give it a little bit of fuel. That'll get you where you're going, and you're not going to build up lead in your guide, and you won't foul your plug. You that have flown already, this is your spark plug. It goes right in here. Every cylinder has two of them, and we'll get into why there's two of them. Every car in the world just about only has one. Airplanes have two. Redundancy, redundancy. When you don't lean, that lead actually builds up inside that plug. Any dirt or debris that's inside this plug is what's fouling out your plug. If you don't lean it, the lead builds up inside the plug and it won't fire. And that's why you get a 200 drop, 300 drop on the mags. It's nothing to do with the mags. If the mag's not firing, you're going to know. A 200, 300 RPM drop is because your plugs are fouled out. Too much lead in the fuel, heat builds up. The lead actually builds up inside here. You'll actually pull out chunks of lead inside the plug. When you look at the plug, you'll know how it's running too, because if it's black, that means you're running rich, and it'll be black. That's the carbon of fuel that's unburnt. But the biggest thing that fouls out these plugs is the lead. Again, why you want to lean in flight and on the ground. Okay? Too much lead, you're going to lose your plugs. You're going to be landing. So, what happens when a plug fouls? When you have an RPM drop on your magneto check, you don't have to cancel your flight, okay? The procedure is to run the throttle all the way in, full power, pull your mixture out, again, to where it starts running rough, and then just give it a little 1/4 inch of mixture. The roughness will go away. That's going to heat up the engine, right? Because remember, fuel cools the engine. Now you're taking the fuel out and you're going to heat up the engine. Why do you want to heat it? You want to try to loosen up the lead inside that plug, cook it, literally burn it, finish burning it, and just spit it out the exhaust. That's what's going to clear out your plugs. So you're going to pull the throttle all the way in, pull the mixture back to where it starts running a little bit rough. You're going to feel it. Listen to your engine. And just give it a little 1/4 inch in. There's nothing scientific here. You got to be one with your machine. Feel what's going on. Listen to it. Listen for noises. Listen to how it runs all the time. This is a lawnmower. Once it's going, it just keeps going. Okay? There is nothing fancy here. It can't get any dumber or simpler than it is. Okay? So, throttle all the way in, mixture till it starts running rough, give it a 1/4 inch in, the engine's going to even out. Just leave it there for 2 minutes. Let the engine get hot. Okay? Go back to your normal procedure, check your mags, guaranteed it's going to clear out that engine. Good to fly. Okay? That good? Plus you're checking that you got full power. Remember, you don't need a lot of fuel. They throw in extra fuel just for cooling. All right? What else? Okay, push rod tubes. There's actually rods in here that are attached to the top end of this valve. Okay? And as that cam turns, there's lobes on there, and it pushes and pulls. Same thing as the cylinder. Opens and closes valves, opens and closes valves. That's all this is doing up here. Okay, you don't want to see a lot of oil, excessive oil leak here. Okay, if there is, there's a problem. It needs to be inspected. Look at your cylinders. Look at the base of your cylinder. You don't want to see oil coming out of the base of your cylinder. Something's gone wrong. Okay, a little drop of oil. There's actually an O-ring at the base of this cylinder. Look, here's the O-ring. I mean, you can't get dumber and stupider than this. Look at that. This is what prevents oil seepage from your cylinder. Okay, it's a stupid little O-ring, right? Like a big rubber band. Okay, if you see a little bit of oil here, its chances are that this ring has failed. Okay, cylinder's got to come out, just put a new 50-cent O-ring in. That simple. Okay, that's what keeps the oil and the crankcase and the cylinder attached. You put metal on metal, it's going to seep oil. This stupid little O-ring just keeps the oil inside the cylinder. A condom for a cylinder. Right. Valve cover gaskets. Not really a lot going on here. This is to keep all this closed up. There's really no oil pressure up here. There shouldn't be. So any oil that's leaking out of this valve cover is just because this needs to be tightened down. Which, believe it or not, with the vibrations this create, these screws actually get loose. Every 1,500 hours, we tighten down those screws. Okay, they always get loose. Right? It's part of an inspection that we do. Right? There's no high technology here. Okay. There's your spark plugs, one on the top, one on the bottom. The plug that generally gets fouled is the bottom one, not so much the top one. So if you got to burn your plugs, you're basically cooking the bottom plug. Why? All the oil and lead, gravity, tends to put it down here. It ain't going to put it up here. All right? These are the plugs that get fouled out, the bottom ones. All right? That's what you're cooking out when you're doing a mag check and you don't have the right drop in your RPMs. All right? Here's your crankcase, again, split in the middle. Most engines have an accessory case on the back. Not all Lycomings have this. This came a little bit later on. There's a lot of things going on in this accessory case. This is really a very important part of this whole engine. This is simple. Crankcase, camshaft, cylinders. That's it. Not a lot of moving parts in here. But in the back here, attached to this cam and crank, there's gears. There's gears that drive this vacuum pump. There's gears that turn with the magnetos. Okay, everything's in time. The magnetos fire right back and back to each other. That's why there's two. This is your ignition system. These magnetos is what turns a very slight voltage from the battery into, like, I think it's 12 or 18,000 volts of electricity to send electricity to the spark plug that's burning the fuel when you're asking it to ignite. So the magnetos are here to create spark, just like a distributor in an old car. Okay, and the new stuff, this has all become electronic. And the newer planes now have more of electronic, but they still have magnetos in them. Some of them might have an electronic system in it. Okay, this works. Okay, when I told you that the keys should be in, shouldn't be in, these magnetos are grounded. They're always active. Every time you turn this prop and you hear that click, you just made a spark. Okay, let me show you magneto. Here's your magneto, right? Here's the gears I was telling you about. I don't want to spark that because I'll get a spark. You see, this doesn't need a spark. It generates its own spark. So if one of you wants to stick your finger in there, I'll show you what 12,000 volts feels like. Any takers? Oh, you know, we used to play tricks on guys. Yeah, can you stick your finger there? You pop that magneto, huh? That click. Okay? That's this impulse coupling right here. That's snapping. It's snapping and generating electricity. Okay, it's very simple. Unfortunately, some of the stuff in here is plastic. Okay, they can break. That's why there's two of them. One fails, you always got another one. The electrical system of the aircraft has nothing to do with the engine. Okay, you don't need the alternator to operate this engine. Once this is turning, the battery is just giving it enough spark to turn the starter, to turn the prop, to get this going. Once this is turning, it's going to keep generating electricity. It doesn't need an alternator, it doesn't need a battery, it doesn't need anything. It is mutually exclusive, for those of you that understand what that word means, from the electrical system of the aircraft. The Cessnas have a split switch for a reason. One is to turn the battery on, and the other one is to activate the alternator, the electrical system of the aircraft. You can turn the alternator off. This engine will keep turning. You're not going to have radios for too much longer, and anything electrical in the airplane will not operate. The battery, if the electrical system of the aircraft is running on the battery, you got maybe half an hour, depending on how much you transmit. Those radios put out 16 watts of power. It takes a lot of electricity to transmit on the radios of an aircraft. It's like a little radio station, okay? The alternator is there to provide electricity for all of this stuff to operate, not the engine. The alternator, which is here, is an accessory to the engine, okay? This is turning to produce electricity for the electrical system of the aircraft. Nothing to do with the engine, okay? You don't need this working for this engine to work. Very important, because you could be in flight, you're going to have problems with the electrical system, you can shut the electrical system down, the engine's going to keep turning. Once this is working, it keeps working. It's dumb, it's stupid, and it doesn't know any better. It's turning and generating electricity, providing juice to the plugs to combust the fuel. That's your ignition system. That's all there is to it. Magneto, cap, wires, plugs. That's your ignition system. That's all there is. Very, very simple, redundant, really just like a lawnmower. Once it's turning, it keeps running. Okay? It's generating its own juice. Okay. Vacuum pump is sucking air, right? Counter rotation has an arrow. As you turn this way, the vacuum pump is actually turning that way, right? Because there's gears in there. It's in reverse. It's not turning in the same direction as the prop. It's counter rotating to the prop. Remember, you only want to turn the prop facing the prop counterclockwise. Do not turn the prop clockwise. This will break. It's plastic in there. A little speck of dirt in the little veins in there, the dirt gets stuck on the vein and it splits the vein and you've lost your vacuum. And it's not going to happen on the ground, it's going to happen in the air. It always happens in the air. It rarely happens on the ground. You'll be flying along and all of a sudden your attitude indicator just starts going really slow. You won't even notice it unless you're looking at it. Next thing you know, your attitude indicator is kind of sideways and you're flying straight. Well, if you look at your suction gauge, you're going to see you've lost suction. First place you're going to see it is either on the gauge or in one of the vacuum-driven instruments, which are the attitude indicator and your directional gyro is being run by this vacuum system. It's just a little tiny vacuum cleaner that's sucking in air, which works with your static air vent over here, right? So here's your hose, very simple. Anything it's sucking out, it's just throwing it out this way, right? 5 psi, 5 pounds per square inch is a norm. Anything from 4 to 6, that represents pounds per square inch. That's all you need, is anywhere from 4 to 6 psi to operate the instrument that are run by the vacuum system. Now, what happens if you have too much vacuum and it goes way past that, or it starts going past that green arc? Well, you're going to suck the life right out of those instruments because they're designed to work at 4 to 6 psi. If you have 8 psi, you're overdriving that instrument and it's going to fail. If you don't have enough vacuum, it doesn't damage the instrument as much, but it's not going to indicate correctly because you don't have enough psi vacuum going through your system. Very simple. Hose, there's a couple of hoses inside attached to those instruments. It's just a closed system of air, right? Sucking. That's your vacuum pump. Some aircraft have electric-driven vacuum pumps as a backup. Almost, I'd have to say 99% is all engine-driven vacuum. You don't get into electric-driven pumps until you get into much higher-end aircraft. But it still works the same. It's there to just suck air. That's all it does, okay?